Lecture, we're looking at population ecology. To understand population ecology, we must first understand what a population is. A population is a group of organisms that are the same species living in the same area at the same time. When dealing with populations, there are a couple of very important factors to consider, and that is population density and population distribution. Population density deals with the number of individuals per unit area or volume. What this means is how densely packed or tightly packed is your population within an area. For example, here's a population map or density map of the United States. You can see that in the Midwest, the population is less than 10 per square mile. They are not very densely packed. However, when you look at the East Coast or West Coast, in some of the dark areas, there are populations of 300 or more per square mile. That is a very densely packed population. Looking at the map this way gives you a better view of that. You can see that cities like New York are extremely densely packed, whereas cities like Rapid City, not so much. The next factor to consider is distribution. Distribution deals with the location of your population in relationship to one another. And there's three types of patterns that tend to arise when you're looking at distribution. Those are clumped, near uniform, and random. Clump patterns are where your members are distributed in patterns in which they are very close to one another, such as a school of fish. You tend to see clumped patterns in populations that are trying to gain some type of protective advantage. Schooling or herding helps these animals better protect themselves from predators. The other pattern is near uniform. Near uniform occurs when your population is evenly distributed throughout a space, such as penguins laying eggs on an island. You tend to find this pattern when resources are limited. The third pattern is a random distribution pattern. This is where members are just randomly distributed throughout an area, such as flowers in a field. When resources are almost unlimited, then you tend to see patterns that are randomly distributed. The next factor to consider when talking about populations is their biotic potential. This is the highest rate of reproduction possible for a population under ideal conditions. In order to be able to determine your biotic potential, you must first understand what your growth rate is. Growth rate is the difference between the amount of individuals born minus the amount of individuals that die. If the number of individuals born is higher than the number of individuals that die, then you have a positive growth rate. If the number of individuals born is lower than the number of individuals that die, then you have a negative growth rate. However, if the number of individuals born equals the number of individuals that die, then you have zero growth rate. Populations that are stable have a very close to zero growth rate. New populations tend to see a positive growth rate. When you have populations that move into a new environment, you tend to see what is called exponential growth. This is unlimited growth of a population. Exponential growth is best described in bacteria growth. Bacteria can divide roughly every 20 minutes. When bacteria divide every 20 minutes, they begin to experience exponential growth. 20 minutes you have 2, 40 minutes you have 4, 60 minutes you have 8, 80 minutes you have 16. At first, the growth rate seems relatively slow, but as you start increasing the minutes, you start to see that the numbers begin doubling quite a bit. And after only 12 hours, there are over 68 billion bacteria. That is a great example of exponential growth. If I graph exponential growth, it looks like this. Starts off very slow, and then it begins to increase quite a bit. This forms what is called a J-curve. Now, exponential growth cannot go on forever. There are certain factors that keep a population from growing out of control. We call those factors limiting factors, and they fall into two categories. They can be density-dependent limiting factors or density-independent limiting factors. Density-dependent factors are the resources that affect population growth as a result of the population's density. These are things such as food, water, and disease. Whereas density-independent limiting factors are factors in which crowding does not influence the likelihood of their occurrence or their magnitude. And so these are things like weather, earthquakes, and other things that are not affected by crowding. Both density-independent and density-dependent factors are both combined to create what's called a carrying capacity. This is the number of individuals in a given population that the environment can sustain. Carrying capacity is often depicted on a graph as an imaginary dotted line. Carrying capacity includes everything from disease to space to predators to food. And so as a population starts growing exponentially, eventually they reach a point at which they have hit carrying capacity, and you will tend to see the population numbers or growth rate level off. This creates what's called an S-curve. Carrying capacity is not a set factor. It can either increase or decrease depending on the factors. For instance, if a predator is eliminated from this organism's ecosystem, then its carrying capacity will increase. This will allow for a higher population number. However, if food becomes so scarce for this population, then the carrying capacity will drop, lowering the population number. We call this type of growth logistical growth. That is, growth with carrying capacity factored in. The next thing to consider when discussing populations is a population's life history pattern. That is, how does an organism in that population allocate its resources? There are two different extremes. There is R-selected and K-selected. R-selected populations are those populations that are adapted to conditions that change very rapidly and unpredictably. They tend to have certain characteristics in common. Characteristics such as shorter development time, early reproduction age, many young per breeding episodes, less parental investment per young, and a high mortality rate. That should read mortality. And a shorter lifespan. Examples of R-selected species would be mice, roaches. K-selected species, on the other hand, are species who have evolved in very stable environments. Their characteristics include longer development times, later reproduction age, few young per breeding episode, a lot of parental involvement and investment in young, lower mortality rates, and a longer lifespan. Examples of K-selected species would be elephants and us. Now, most species do not fall within one extreme or the other. Many species have characteristics that fall somewhere in between. And so when we look at an organism's life history pattern, we look to see towards which extreme do they lean. And that is all for population ecology. I hope this was helpful.